So for this question, the first thing to do is to make sure that you expand r sine theta minus alpha correctly. You may know it, but you can always use the formula booklet to help you. So that will be r sine theta cos alpha, take away r cos theta sine alpha. Next, you're going to put the expression you've been given equal to that expansion. So we have 8 sine theta minus 15 cos theta is the same as r sine theta cos alpha minus r cos theta sine alpha. And now, because it's an equivalence, so it's true for all theta, the coefficient of sine theta on the left must equal the coefficient of sine theta on the right, and similarly for cos theta. So that allows us to say that r cos alpha is equal to 8 and r sine alpha is equal to 15. And the reason I wrote them sort of upside down is that reminds me that I can divide those. The r's will cancel and I'll be left with sine alpha over cos alpha, which is tan alpha, and that will be 15 over 8, giving me alpha equals 61.93 degrees to 2 decimal places. Now to find r, we again use these two equations here, and we remember that, first of all, sine squared of an angle plus cos squared of the same angle is always equal to 1. So then we can square each of those. So we have r squared sine squared alpha plus r squared cos squared alpha must be equal to 15 squared plus 8 squared. That means r squared times sine squared alpha plus cos squared alpha is equal to 15 squared plus 8 squared. And because of the sine squared plus cos squared being 1, that leaves us with r squared equals 15 squared plus 8 squared, which is 289, and therefore r is equal to 17. Now, in an exam situation, I think it's a good idea to write this stuff, perhaps not the top line, so maybe not that one, because that really should be totally known at this stage in your career, but the other two lines, they're not necessary. If you've done enough practice of these, you'll know that r squared is going to be the two numbers squared and added, so sort of Pythagoras situation. But for safety's sake, you may decide to put one or other of these lines in, just to make clear. Anyway, we've now found what r is, we've found what alpha is, so we can say that 8 sine theta take away 15 cos theta is the same as 17 sine theta minus 61.93. Not quite the same, of course, because we've rounded off the angle, but it's close enough. If at this point you wanted to check, you could put a random angle in and see if it works. So, as I've mentioned in some of these videos, you might make a little mark here, and you could put, I don't know, 100 degrees in, whatever. So we could try 8 sine 100, take away 15 cos 100, and that comes to 10.483 to 3 decimal places. And then you would put the same number into the other side, which would give you 10.483 also. They don't match exactly because of the rounding off here. Nevertheless, that's enough for you to feel confident that you've got it right. So for part B, we use what we've just done, and we're given that 8 sine theta minus 15 cos theta minus 7 equals 0. This we can replace by what we've just done. So we have 17 sine of theta minus 61.93, and then we'll add 7 to both sides, so we put that on the other side. That then gives us that sine of theta minus 61.93 is equal to 7 over 17. Therefore, theta minus 61.93 is sine to the minus 1, or inverse sine of 7 over 17. Now, since we have theta being between 0 and 360 degrees, then theta minus 61.93 will be between minus 61.93 and 298.07. So with our calculator we find that sine to the minus 1 of 7 over 17 is 24.32, but then we need to think about the sine curve, and coming from in the negative, so we've got our 61 minus 61.93 is about here, and then 298 is about here, and we need this to be 7 over 17, which is about here. So our two answers are here, which is our 24.32, and here, which is 180. That's a terrible 2. 180 take away 24.32, which we can then put next to this one, which is 155.68, and that means that we get theta equals 24.32 plus 61.93, or 155.68 plus 61.93, which gives us our two answers of 86.24 or 217.61. Now, either at this point or towards the end of the exam, or at the end of the exam when you're checking back through, and you could put a mark to remind you that there's an easy check here, you could take one of these values and stick it back in the original equation, make sure it works. So you'll type into your calculator 8 sine, I'm going to use 217.61, minus 15 cos of 217.61, take away 7, and this gives me, just rounding off, 4.8 times 10 to the minus 4, which is tiny, and it's not quite 0 because we rounded off the angles, but it's close enough to 0 to make us feel confident that we've got the right answer there. Part C is another application of the work you did in Part A. So we want the maximum and minimum values of this thing, 8 sine theta minus 15 cos theta plus 23, and that is the same as 1 over 17 sine of theta minus 61.93 plus 23. Now, for the maximum value of this, we want to make the bottom as small as possible. So we want the minimum value on the bottom. The minimum value of sine is minus 1. So our maximum is 1 over 17 times minus 1 plus 23, which comes out as 1 over 6. And our minimum value will come from maximising the bottom. So that means taking the maximum value of sine, which is 1. So that gives us 1 over 17 times 1 plus 23, which gives us 1 over 40.
On Geogebra, we can have a look at this question. And the first thing we can have a look at is the harmonic form. So that is the form r sine theta minus alpha in this case. So we have two trigonometric curves, a sine curve, which is our 8 sine x, and our minus 15 cos x in the blue. And what we can see is if we drag this point along, it'll drag the other points, and we can see what happens with the harmonic form. So at the beginning, the green, which is representing the harmonic form, is at minus 15 because the sine part of it is 0. But what we can see here is both curves are increasing, and so the negative value of the b is going to decrease until we get to this point here where the cos is 0 and the sine is at the 8 sine is at 8. At that point the harmonic form will meet the sine curve. So let's have a look at what happens. So up it goes to there, and now at this point the cos curve is increasing rapidly, whereas the sine one is decreasing relatively slowly. So the green curve will carry on going up. Around here the sine is decreasing more quickly than the cos is increasing, so this will come across. So let's drag the s. So the increase in the harmonic form is starting to diminish, and we get to a maximum about there, and it starts coming down. Of course here it meets the 15 cos curve because the sine curve is at 0, and then we can go down, and it's quite easy to make this Geogebra if you want to, or your teacher can supply you with a copy of it, and we can see how it carries on in a similar way, and so on. Now what we can also do here is we can have a look at part B. So we can pop in the line y equals 7. So if 8 sine theta minus 15 cos theta minus 7 equals 0, then 8 sine theta minus 15 cos theta must equal 7. And so we can see the intersection points here and here, to the only two between 0 and 360, and sure enough they are giving us the angles 86 about here and 217, which is about here. Another interesting thing, which is beyond this question but related, is that if we have a phase difference between the two trigonometric curves, well, let's see what happens. So this delta here is included now in the cos part. So it is actually cos of x plus delta. The delta will show up when we increase it from 0. So this is going to be cos x plus delta. So that's of the form f of x plus delta. And so, as you may know, as delta increases, the curve will move to the left. So let's see what happens. So The blue curve is moving to the left. So if I go to 45-ish, then we have this, and we can see that the 90 degrees that the cos curve was at 0 has moved across to about 45. And we can see as we slide it along that the harmonic form is changing. Its magnitude goes up and then down again, but its essential form is staying the same. It's still a trigonometric sine stroke cos curve. Go back again. There we are. Okay, so now we'll have a look at part C. So for this, if we show the harmonic form, we can remove the original curves now, and if we move that up by 23, then it looks like this. We can see that that's gone from minus 15 to plus 8, so it's gone up 23. And now we'll remove our original harmonic form by clicking on here, and we can now do 1 over this curve, which looks like this. And first of all, the plus 23 is needed because otherwise we would be going across 0, and then when we did 1 over that, we would go to infinity. So moving it up the original function by 23 means that when we do the reciprocal, it's all positive and doesn't cross 0, so we don't get an infinity problem. Now you can see that this is a very flat sort of curve. I shall expand it in a second, but what we can see is, of course, it is periodic because the original functions are periodic, and it's rising up here, and we can see the maximum is here for the original with the plus 23, so that's going to be the minimum. So if we now expand, doesn't matter where we do, expand it there, and we can change the ratios. Okay, and we can see that we get this, I think of it as a fried egg, just my image for it, and there we have our maximum, which is 1 over 6. In fact, we could push the boat out. There we are, that's better. So that's at 0.16666, and we can see the minimum down here, which is actually 0.025, which we can see makes sense on this scale. So that's part C.
Another little extra for this question is a proof of the compound angle formula sine alpha plus beta. This proof is geometric and is only for the situation where alpha plus beta is less than 90. As you can see from the diagram, we have alpha here and beta here. From the diagram we can see that the sine of alpha plus beta will be the opposite, which is BD, over the hypotenuse, which is OB. Now we can also see that BD is equal to BX plus XD. Now if we look at these angles and chase them round a bit, XA is parallel to OE or DE, and so we have a Z angle which gives us an alpha here. That also means that the angle at A here is 90 minus alpha, and therefore this angle here is alpha. Now that means that in triangle BXA we have that BX over BA is cos alpha, and therefore BX equals BA OA cos alpha. In the triangle OAE, since XD is equal to AE, we have that XD over OA is sine alpha, and therefore XD equals OA sine alpha. Now we can now substitute these into equation 1, and that gives us that BD equals BA cos alpha plus OA sine alpha. Now we can then replace the BD in our original equation up here, which gives us sine of alpha plus beta equals BA cos alpha plus OA sine alpha, and because it's all divided by OB, we can just divide each part by OB. Now at this point, notice that I said earlier that this dotted angle here was 90 minus alpha, and that's because we actually have a right angle here that when we constructed this diagram. So we can now look at the triangle OAB, and we get for that triangle that BA over OB is the opposite over the hypotenuse in the triangle with the angle beta, so that gives us sine beta, and OA over OB is the adjacent over the hypotenuse in that triangle, so that gives us cos beta. And so finally we can substitute those back in, and we get sine of alpha plus beta equals sine beta cos alpha plus cos beta sine alpha, which is what we wanted. And you can do similar geometric proofs for the cases where alpha plus beta is greater than 90 as well. So there we are. You may have seen proofs of the compound angle formulae before, but if not, there's one of them at least.